Good morning, class, and welcome to this lesson on Modern 7 History of the Atom and Bohr's Model. Today, we'll be able to explain the major developments in the history of the atom and conclude with Niels Bohr's model. So, this is going to be a very, very brief history lesson. I'm not going to get into each individual or their experiment in depth. I'm just going to cover it real quick because the real point is I want to get to Niels Bohr model and talk about how that relates to quantum mechanics. Okay, so long time ago, there was a man named John Dalton, and he concluded that the atom is the smallest unit. Now, before him, when they thought about atom or elements, they thought about, they're going way back before that. They're talking about like Earth, Earth, wind, the elements of nature, not so much the elements of different types of materials. So John Dalton was the first to discover that the atom is the smallest unit, the unbreakable unit. So after him, there's a man named J.J. Thomson, and he discovered with his cathode ray tube. If you want to know more about it, I suggest looking up other videos on it. There's a lot of information on it. And he discovered that there was electrons. And so basically, J.J. Thomson discovered that the atom is not the smallest unit, but there are subunits of the atom, and one of those subunits is the electron itself. And so once he discovered that, he developed a model for the electrons, and we call it the plum pudding model. And this plum pudding model is just like this. Basically, the atom is like pudding, and the pudding is like positively charged pudding, and then the electrons are inside it like plums, and they kind of balance out the whole thing. So this would equal a neutral atom, but these negative electrons before them, um, these negative electrons balance out the whole pudding. So there's just one big unit like this. Okay. Now, later on, there is a man named Ernest Rutherford, and he had his gold foil experiment, where they were firing particles at gold, and what they found was that most of these particles went straight through. They went straight through the gold. Some got deflected. You can see here some got deflected, and some even came almost straight back. Okay, but most went straight through. So based off this, he concluded that there is a nucleus, a very small, very dense nucleus. This nucleus is positively charged, and there are electrons orbiting the nucleus. There are electrons orbiting the nucleus, and these electrons take up a lot of empty space. There's just a lot of empty space there. And that was the significance that many of these particles are passing straight through. The fact that this gold looks solid, but the reality is because these particles are passing straight through, most of this gold is actually empty space because there is a lot of space in between the nucleus and the electron in between it. This is very small and very dense. The nucleus makes up about 99.9% of the mass. And the electrons are orbiting very, very far around it. I once heard a good analogy. If the nucleus was the size of a grain of sand, if we were able to blow up the nucleus and it was the size of the grain of sand, the electron would orbit about a football field's length, so about 100 yards, away from it. So if the nucleus was the size of a grain of sand, the electron would be about 100 yards away from it. Okay, so that is how much empty space there is in an atom. However, most of the weight is concentrated right here in the center. The issue with this model is simple. Oh, by the way, this is called the planetary model. This is called the planetary model because it's kind of like our solar system. The issue with this model is very simple. If electrons are accelerating, if electrons are accelerating, they should be giving off EM radiation. Okay? So as they accelerate, they should be giving off energy. Well, if they're giving off energy, they should slow down. And if if the nucleus is positive and electron is negative, then electron should crash into the nucleus. So Rutherford knew his model was incomplete, but he knew that they're one step closer than the plum pudding model. So basically, according to his model, an electron should orbit around and eventually come crashing into the nucleus. We know this doesn't happen because this would be an unstable atom. This would be unstable, but we know there's atoms are stable, so that's not true. So if electrons are accelerating, they should be giving off EM radiation or energy. They should slow down, and the positive and negative forces are very strong. Electrons should crash into the nucleus, but they don't. So this is an issue. Well, this was later resolved by Niels Bohr, and Bohr's model had four main points. Electrons are in circular orbits. Okay, this is similar to Rutherford. Okay, an electron has a definite energy without giving off EM radiation. Okay, this is a little bit different. Okay, electrons transition from different energy levels. Radiation is emitted or absorbed during this process. Okay, so there are energy levels. This is something new, and only certain orbits are allowed. So notice we're talking about levels. We're talking about definite energy. Basically, we are adding this idea of quantum mechanics to this idea of Ernest Rutherford's model. So, just like an electron receives a photon of energy to be emitted, to be ejected from an atom, this is kind of the same thing. Electrons can only absorb or emit certain amounts of energy. Only certain amount of orbits are allowed because only certain amount of energy levels can emit or absorb energy. Okay, so we are back to this idea of quantum, of these discrete values. Discrete values. Okay, so this is the Niels Bohr model of the atom, which is very similar to Rutherford, where electrons have energy levels and they can only transition from level to level. Okay, and so if an electron is going from a higher level to lower, it's going to emit a photon or give off energy. Okay, if it's going from a higher level to a lower level, it's going to give off energy. And the opposite, if it's going from a lower to a higher, it's going to absorb energy or absorb a photon. So in this picture, if I put the electron right here and it's going from here to here, then that's going to be because it gained a photon. Okay, a very, very specific photon because it only can go from level to level. Okay, so this kind of solved the problem with Rutherford's model that the electron is not going to spiral inward because it only can give off or absorb certain energy levels. It's not going to lose them. It's not going to have a steady loss and come crashing into the nucleus. Now, Bohr's model is still not the #1 model we use anymore because Bohr's model, I'm just going to say this now, Bohr's model only works truly for the hydrogen atom. Because a hydrogen atom has one proton and one electron. Okay, has one proton and one electron. So Bohr's model is perfect for the hydrogen atom. Once we go past the hydrogen atom and we have two or more electrons, there are forces there with two or more electrons that Bohr did not take into account. And so this model still works. These electrons still have to absorb discrete energy levels, but it's not going to be as exact with other atoms because of the fact that there's forces that he did not take into account. But for the purposes of this class, we're going to stick with Bohr's model to gain an understanding of how this energy level system works, because we want to learn simple first before we get more complicated. And so this is kind of like in mechanics, like when we ignored friction. We know that friction is always there, and but we ignored it because we wanted to make the math simple and we wanted to gain the concept. So right now we're going to stick with Bohr's model and get the concept from him, and then later on build up. Maybe not for the purposes of AP Physics, but later in your physics careers.